Okay, picking up where we left off with the displacement of the skier question, we saw that there were three segments to the journey. The first one is 5 kilometers north, second one is 3 kilometers west, and then the third one is 4 kilometers southwest. And we've basically found the angles, and we break the journey up into its segments. Each one represented by a separate vector. And we found the x and y components for the vector for the first segment. The magnitude of the vector for the first segment will just be the x component of the magnitude for the first segment plus the y component for the magnitude of the first segment. And where we left off is we were about to do the same for the second leg of the journey, or the second segment. The magnitude for the second segment is just, again, the total of the x and y components of the magnitude for the second segment, d2x and d2y. So d2x, the x component of the second segment vector for the journey, would just be the magnitude of the second segment, that is the distance, times the cosine of the angle. In this case, the distance was 3 kilometers, and the direction was west, which again is 180 degrees. So 3 kilometers times cosine of 180. And that comes to negative 3 kilometers as the magnitude of the x component of the second leg of the journey. The y component is going to be the distance, length of the second segment of the journey times the sine of the same angle. And so that's 3 kilometers times the sine of 180. And that is 0 kilometers because the sine of 180 is 0. So there are the x and y components for the second segment of the journey. We do the same for the third segment. The magnitude of the third segment is just equal to the x and y components of the third segment. So the x component of the third segment is going to be the distance of the third segment, which was 4 kilometers, times the cosine of the angle of the third segment. The direction was southwest, and we figured before that the angle for southwest, measuring from the positive x-axis like we normally do, would be 225 degrees. So this is 4 kilometers times cosine of 225, which is negative 2.83 kilometers. The y component would be that distance, again, the distance of the third segment times the sine of the angle of the direction. So that's 4 kilometers times the sine of 225. And that comes to negative 2.83 kilometers, because it turns out the sine and cosine of 225 are the same. Okay, so the x component of the overall displacement vector is going to be the x component for the first segment plus the x component for the second segment plus the x component for the third segment. So that's just going to be 0 plus negative 3 plus negative 2.83, which we see here. And that comes to a total of negative 5.83 kilometers. The y component of the overall displacement vector is going to be the y component for the first segment of the journey plus the y component for the second segment plus the y component for the third segment. So that's going to be 5 plus 0 plus negative 2.83, which is 2.17 kilometers. So you can write the equation for the vector of the overall displacement. So that's what we've got here. The overall displacement vector is going to be negative 5.83 times unit vector I plus 2.17 times unit vector j kilometers. Okay, so that is the displacement vector. The return vector would just be the negative of that. In other words, it has the same magnitudes, but it's in the opposite direction. So we just take the negative. Essentially, it's the same as taking this vector and multiplying it by the scalar -1. So you just change the signs. So the return vector would have an equation of positive 5.83 times unit vector I minus 2.17 times unit vector j kilometers. Okay, so that's the equation for the return vector. What we were actually being asked for at the beginning of the problem was the magnitude and direction that they would have to use in going back towards the lodge. The magnitude of the return vector, here R means return, it doesn't actually stand for resultant like it usually does, would be just the square root of the x component of the return vector squared plus the y component of the return vector squared. And these are the x and y components. So that's 5.83, a square root of 5.83 squared plus negative 2.17 squared is the square root of this, which is 6.22 kilometers. So that's the magnitude. That's the distance. The direction, theta r, we'll call it, for the angle of return, would be the inverse tangent, or in other words, the angle whose tangent is the y component for the return vector over the x component for the return vector. Okay, make that a little clearer. So that's the inverse tangent of negative 2.17 kilometers over 5.83 kilometers. Kilometers over kilometers cancels, so there's no unit. And the angle whose tangent is negative 2.17 over 5.83, whatever number that comes out to be when you divide that out. The angle is negative 20.42. Or in other words, 20.42 south of east. Whoops. You could also, if you wanted to, do this the conventional way. And it would be (339.58 degrees if you're going counterclockwise from the positive x-axis. Okay. Okay, the next example has to do with displacement of a jogger, where you have a jogger who runs up some stairs, 200 steps to be exact, to the top of a hill, and runs along the top of the hill on level ground for 50 meters before stopping at a drinking fountain. Displacement vector from the bottom of the stairs, which is point A, to the fountain, point B, is given by this equation, DAB, and I've drawn a little diagram of it here. The person starts, very well drawn jogger there, starts at point A, goes to the top of the stairs at point T, presumably for top, and then continues to point B, where he stops for a rest. The vector going directly from A to B, which would be basically this vector here, is given by the equation negative 90 I plus 30 J meters. So what they want to know is what's the height and width of each step going from point A to point T? And what is the actual distance covered from point A to point B? So in other words, you've got this distance plus this distance here. That would be the total distance covered from point A to point B. And if he makes a loop and returns to part A, what would his overall net displacement vector be? Actually, that one right there, that last question, we should be able to answer that without doing any work at all. Because remember, whenever you end up where you started from, your net displacement is 0. So if he makes a loop and returns to point A, regardless of what route he takes, his overall or net displacement will be 0. So we got that part done right up front. Okay, so if we look at the little diagram that we've drawn here, and there's a better diagram in the book if you want to look at it, the vector from A to B is actually equal to the sum of the vector from A to T plus the vector from T to B. We want to find the horizontal and vertical components of the vector from A to T. And the book got this wrong, actually. I wasn't looking at the book, and I originally wrote down AT here, and then I noticed the book had TB, and I crossed out and wrote that down, and then I looked at it and said, oh, wait a minute. The book is wrong on that. I was right the first time. It's actually, you want to find the horizontal and vertical components of vector AT in order to find the height of the steps, because that's where the steps are between A and T, right? I don't know where they got T and B. I guess the reason the book's so cheap is because they didn't hire any proofreaders. Anyway, each step has a width W and a height H. The horizontal component of the vector from A to T is 200 W in length, because it said 200 steps, and they're all the same size. So if we let W represent the horizontal component, then the horizontal component would be 200 W, and the vertical component would be 200 H. Okay. And so let's see, the jogger's displacement vector when he's at the top of the hill would be vector D TB. TB, go between the top of the hill and the point B, would be negative 50 meters I. And there's no J component because this is on level ground. It's entirely in the X direction. So the the Y component just falls out. The net displacement vector DAB, that is from point A to point B, is going to be the total of DAT from A to T plus the vector from T to B, which is what we're saying here. And so you can rearrange this to find D from A to T by just saying, okay, algebraically, if this is true, then the vector from A to T must be equal to the total distance, that is the vector from A to B, minus the vector from T to B. And we've got both of those vectors. The vector for the points A to B is negative 90I plus 30J meters. And from that, we're going to subtract the vector for TB, which is right here. So it's minus negative 50 meters I. And so you combine the I terms, minus 90 plus 50, that is minus a negative 50 would be plus 50, minus 90 plus 50 is minus 40 I plus 30 JM. So that is the vector from A to T. Okay, so the X component of that vector from A to T would be negative 40 meters. And the Y component of that vector from A to T would be 30 meters. Okay, so the width and height of each step, well, we've got 200W, that's the horizontal component, and that is equal to 40 meters. And with the directions we're using here, it's negative 40 meters, but of course, negative just indicates a direction, and 40 would be the magnitude. And so we take the absolute value of the negative 40. 200W equals the absolute value of negative 40 meters. And when you solve for W, you just take 40 divided by 200, that's 0.20 meters, or 20 centimeters. So each step is 20 centimeters high, or well, 20 centimeters wide, sorry. 200H is the vertical component from going from A to T. And the Y component, that is the vertical component, has a distance of 30 meters. So 200H equals 30 meters. And so we can find H is just 30 meters divided by 200, which is 0.15 meters or 15 centimeters. So those are the dimensions of the steps. And if we want the total distance covered from A to B, we've got the distance from T to B, that's 50 meters. We don't have the distance from A to T though. What we want for this is the horizontal distance going up the stairs. And again, drawing it the way I've drawn it here, I haven't drawn it terribly carefully, but hopefully you can tell from my fractured artistic skills that what you've got here is a right triangle. And the distance from A to T is the hypotenuse of the right triangle. And so we end up using the Pythagorean theorem to find the distance from A to T. It's just the x component, the square root of the x component squared plus the y component squared. Okay, and that's what this is, dAtx squared plus dAty squared. Take the square root, and we have square root of negative 40 meters squared plus 30 meters squared, square root of 2,500, that's 50 meters. So 50 meters diagonally up the stairs and 50 meters straight across from T to B means that the total distance is 100 meters. And the final point is the one I made at the very beginning. Just remember, if you end up at the same point you started from, then your net displacement is going to be 0. So if it returns to point A, the total distance would be 200 meters. That is 50 plus 50 plus 50 plus 50. So that's the distance, but they weren't actually asking for distance, they were asking for displacement. Like I said, if you start at the same point, or if you end up at the same point you started from, your displacement is 0. And it doesn't even matter if he took a different route back. Still 0. Whether he took a different route back would matter for the distance. We're assuming he took the same route back. If he took a different route back, then we don't know what the total distance is. But the displacement would be 0 either way. Same route, different route, doesn't matter. If you end up in the same place you started from, your displacement's 0. Okay, oh, well, we have a few more minutes left. So let's see. In looking at the direction of a vector, you can use the unit vector to signal the direction of a vector if the vector is along an axis. So for instance, the direction of the vector A, if that's equal to negative 15.3 meters times J, sorry, that should be the unit vector J. the direction is negative j. The 15.3 meters is the magnitude, but the direction would be negative j. So mathematically, general rule for finding a unit vector direction for a vector is just divide it by its magnitude. Or in other words, the unit vector for a vector would be equal to the actual vector divided by the magnitude of the vector. So v with a hat on it is the unit vector for vector v. V with an arrow over it is the actual vector v, and v with nothing over it is the magnitude of vector v. Keep in mind that the unit vector has no units, because the units for the vector and for the magnitude would be the same, so they cancel out. And a good example of that is example 214. This up here, what we've seen of it up here is very simple and may seem pretty obvious. But 214 sort of takes that principle and extends it quite a bit to a situation where it might not be so obvious. So let's see, this harks back to an example that was quite a while ago where we had a military convoy that was traversing some territory. And if the velocity vector for that convoy is 4 times unit vector I plus 3 times unit vector j plus 0.1 times unit vector k in units of kilometers per hour, what would be the unit vector of its direction of motion? This is a little harder because up here they were basically just showing you a vector that only had one component. What do you do if there's 2 or 3 components to the vector? Then what do you do? Well, what you still have to do is find the magnitude of the 3 vectors together and then divide each of the magnitudes of the 3 directions by the overall magnitude. That's essentially what we're going to do here. So the unit vector of the velocity vector would be v with a circumflex, or a caret, or a hat, whichever you like to call it. And it would be parallel to the direction of the velocity vector. And so we just want to divide the velocity vector by its magnitude. But we have to find its magnitude first. But remember, the magnitude of a vector is just the square root of the x and y and z components squared. So the magnitude of vector v is just going to be the square root of 4 squared plus 3 squared plus 0.1 squared, which is the square root of 25.01, which is 5.001 kilometers per hour. That's the magnitude of the velocity vector. So if we want the unit vector for this velocity vector, we just take the equation for the vector and divide each of the terms by the magnitude. You can do it first by taking the entire equation and dividing it by the magnitude of the overall vector. So it's 4 times unit vector I plus 3 times unit vector j plus 0.1 times unit vector k kilometers per hour divided by 5.001 kilometers per hour. And you can then take each of those terms separately divided by the magnitude. And I've dropped the units because kilometers per hour will cancel with kilometers per hour. So the I term would be 4 divided by 5.001, which is 0.7998 times unit vector I. The j term would be 3 divided by 5.001, which would be 0.5999 times unit vector j. And the k term would be 0.1 divided by 5.001, which is 0.02 times unit vector k. And so this is the unit vector for the velocity vector that we started out with. Okay, so it sounds complicated, but when you actually see an example done, it's not so bad. You just use the Pythagorean theorem to find the magnitude of the overall vector itself, and then you divide each term of the vector by that number. And then what you get will be the unit vector. Okay, I think that's just about enough to bring us to the end of this segment of the video. We'll get into vector products in the next lecture. So there's something to look forward to. Until next time, see you later.